This week started off by Jacopo telling us about various things about neutral theory and stochasticity. Please, Jacopo.
Yes, thanks a lot. So, welcome to the second week. Just to have, before I start with today's lecture, just to have a little plan for the lectures that I'll deliver. So the broad goal of these lectures will be to show you how stochasticity, so randomness, which is something we have not seen in the past week, impacts community structure and dynamics. And so there is a long history in ecology including stochasticity. And the idea is that what we have seen last week was like mostly deterministic dynamics. What does it mean? That if we start with some initial condition and we follow the dynamics for that initial condition, we end up with some deterministic solution. Okay. Now this deterministic solution can be simple, can be a fixed point, can be more complicated, can be a chaotic attractor, but somehow there is a deterministic map between the two. What I want to show you is what happens if we include stochasticity, so some sorts of randomness in ecological dynamics. And now these lectures will be divided in 3 parts, so the 3 lectures. So today, it's a sort of tutorial on stochastic processes, but sort of to get used to the language of stochastic processes. And in doing so, we are going to use example from basically what can be thought as stochastic exponential growth. So I'll show you 2 examples in which exponential growth, so the simplest ecological dynamics you can imagine is stochastic. And I want to show the message of today. What I want to convince you is that stochasticity is not just a noise on top of the deterministic solution. So that can really change the property of the dynamics. Okay, it's not just a perturbation. So today is the 13th. So tomorrow, what we're going to do is introduction to neutral theory, which is basically a very, let's say, influential model of set of models, which is based on the assumption that what we see is exclusively dominated by stochasticity. So somehow there is no deterministic force, and the patterns that we see of diversity, of abundance, of variation are dominated purely by stochasticity. And then on the 16th, what I'll try to describe are sort of patterns in microbial ecology and how we can try to describe them using environmental stochasticity. So this is sort of the plan. So today, as I said, is this double goal of showing you the stochasticity matters, but also introducing you to stochastic processes. So before I start, I have one question and one sort of comment. So the comment is, of course, this is especially for today, but it's valid for all the day. This is a tutorial. So the goal is that we try to be all in the same page. So if I say something that you don't understand, don't be shy to raise your hand and say, I have no idea what you're saying. Or, I mean, this should be more of a kind of a discussion, even if I'm on the stage and you're looking at me. So let's try to have as many questions and stop me as much as you can. The second question that I have is, how many of you have seen, just to have an idea of where we stay, how many of you have seen random walks in your, okay, perfect. Okay. So for those that have not seen random walks, do you have an idea of basic concept in probability? So what is a probability? What is independence, bias theorem? Okay. Now, of course, it's very hard if I ask, is any of you not aware of what this is? Because this is a way to, but okay, so since most of you have have seen the random walk, I think we can start from that. Okay. The other thing I wanted to say is that I have some sort of lecture notes that I'll share, and I'll share the link to you after the class. So all the derivation, the sort of details are in the notes, so you don't have to sort of write like a crazy person trying to write all the derivations, because everything is there. So try to follow I will not do very long derivations, but try to follow the concepts and the structures that I'm doing. Okay. Questions? Okay. Good. Okay, so let's start with the basic concept of what is a stochastic process. So the ingredients, so let's see, stochastic. So what are the basic ingredients of a stochastic process? There are two basic ingredients, okay? One is that we have some configurations, and we can call a configuration C. And the other one is that we have some transition rates. So something that tells us what is the rate to go from a configuration and another configuration. Now, to give you an example, if you have a random walk, what are the configuration? Actually, let me not give you an example. You give me the example. If we have a random walk, what is a configuration? Exactly, it's a position in space. And what is the transition rate? Yeah, so it's the rate. So what is a rate? So the rate is a probability per unit time. Okay. So if you want the probability that, so a probability is in a small time delta t is the rate. So this is a probability. So the rate is a probability per unit time that we're going to go to a configuration C to a configuration C prime. So in the case of random walk, if I'm an unbiased random walker and I'm on this line, the rate is the probability per unit time that I'm going to go left, or the probability per unit time that I go right. And of course, these two can be different. Okay? And now these are the ingredients. So what is the question that we typically ask when we have a stochastic process? So of course, when you have a stochastic process, we can imagine to generate this trajectory, right? If I'm a random walker, so I'm here, I can say, okay, per unit time, I will move. So perhaps I move here, then I move here, then I move here, and I can generate one of these trajectories, right? But all of these trajectories are, by definition, stochastic. So if I generate a new trajectory, it's going to be a different trajectory. So what we are interested in study is something that we can solve and we can describe, we can use to describe this process. So the question that we typically ask when we have a stochastic process is, what is the probability of being in configuration C, say, at a given time t, given that we are in a configuration 0 at time equal to 0. Okay? So we say if I start here, what is the probability that by doing this, I mean, actually, when I teach, I do random walk. So if I start here, what is the probability that in, I don't know, 10 minutes, I'm going to be there instead of here? Okay? Questions about this setting? Is this clear? Okay. Now, of course, this is the thing we want to solve, we want to study. So in order to study it, we want to write an equation that describes this probability, how this probability change over time, as a function of what are the ingredients of our process, right? So somehow the space in this configuration live. So for instance, now we said we consider the case of the random walk, but in general, in ecology, we will not be interested in the random walk, and for instance, we will be interested in abundances, right? So in that case, our configurations will be abundances, so which typically in the world that we live are non-negative numbers. So we will have abundances, and we want to know what is the abundance of a given species in a given time in the future, right? But you can be interested in other processes. I don't know, if you are interested in the financial market, this will be the value or the price of a given asset, and so on and so forth. Okay, so what we want to do is to write an equation for this probability. Okay, so what we want to know, the way to write this equation is to ask, what is the probability of being in a configuration C at a time t plus delta t, given, well, starting with the initial condition, okay? And actually, for simplicity, I'll drop this dependency and say that this is somewhat implicit in my probability, okay? So what is the probability of being in configuration C at times t plus delta t? Well, it will be the probability of being in C at time t, right? Plus the possible changes, okay? So what are the possible changes? So this probability, the probability of being in configuration C, of being here in space, will be the probability that I was here previously, plus the probability that I was not here and I arrived to this point, right? So this is the sum of all the configuration C prime of the probability that I was in C prime at time t, and then I went from C prime to C in this step, okay? So the probability that I here at some time in the future is the probability that I was here, plus the probability that I was somewhere else and arrived here in this time delta t, minus the probability that I was here, but I went away, okay? So this is what is the probability that I was here and I went away. This is the probability that I was in C at time t times the rate at which I go from C to C prime times delta t. Okay? Any question?
Depend on the size of C prime minus C.
For now, I'm saying this in a very general setting where C and C prime can be arbitrary configuration, right? So what you have in mind in asking this question is that, for instance, I'm on some space, right? Well, on this one-dimensional space, which is this stage, and somehow the probability of going from here, or the rate at which I go from here to here, or the rate at which I go from here to this point here, depends on the distance, right? It could, but this is a very general setting where C and C prime can be pointy space, right? I could imagine that I'm doing a random walk between sites that are connected by, I don't know, between islands that are connected by bridges, right? And you can have something very complicated when basically you can be connected or not connected, but there is not a clear notion of distance, okay? Did I answer the question? Yeah, okay. Now, what I'm gonna do with this is a question. What I'm gonna do with this? What do you think? When you see an equation like this, what is the next step usually? Yeah, so I take this part, I put it here, and I divide by delta t, okay? So I write P of C of t plus delta t minus this term, I divide by delta t, and then what do? I take the limit for delta t being very small, okay? So if I do that, what I get is an equation that reads write it like this. Okay, So this equation here, it's called master equation and describe the properties of a stochastic processes. Okay, fully defines the dynamics of a stochastic process. So who is familiar with this? Okay, good. Okay, now this equation is as general, as sort of complete, as somewhat useless, in the sense that you'll never be able to solve this equation as it is. Okay, so it fully defines the process, but you always have to do some tricks to solve it. Okay, now in order to sort of get used to this, I was thinking of deriving this and studying this for the random walk, and then to consider the other scenarios. Okay, so let's consider the case of a random walk on a one-dimensional lattice. Okay, so what we have is that we have positions in space. Okay, which we can represent as the integers, and we have some rate. So we are in a position, let's say n, and we have some rate at which we go to the right, and some rate at which we go to the left. Okay, so in our case, our configurations are, if you want, the integers, and there are two rates. So the rate at which we go to from n to n plus 1, which will be equal to this lambda plus, okay? And the rate at which we go from n to n minus 1, which is equal to lambda minus. Okay? Very good. So in this case, it's very simple to write the master equation, which will read something like this. So it will be, so I have to first write this part here, which is the probability that I was n minus 1 at time t, right? This is one of the two configurations. So in this case, all the rates are only between neighboring sites, right? So all the other rates, if you want, the rate of going from n directly to n plus 2 is equal to 0, okay? So when I sum, I have this term plus lambda minus n plus 1 t, okay? And then I have minus the rate of going away, which is equal to lambda plus lambda minus p of t. Questions? Yeah. No, I'm taking, so this is like, if you want, is in continuous time, okay? So I'm not taking delta t to be 1, so these are rates, okay? So this is the probability per unit time. And I'm assuming, I mean, this is exact, there is no approximation here, okay? When you write this equation here, okay, this equation is correct only if delta t is very small, right? Because only if delta t is very small, you are saying in a small amount of time, the only things that can happen is that either I don't move or one event occurs, okay? Because if delta t was large in a finite amount of time, suppose that you have that process, I could move of 2 steps, right? While here I'm saying delta t is so small that either I don't move or I move of 1 step. Okay? Good. Okay, now, who knows how to, well, how do you solve this problem of the random walk? Okay? So there are many ways. I want just to tell you 2 ways, and I will not do the derivation, and it will be on the notes, but so you have an idea of how you can go. So one way is that you don't consider directly this equation, but what you realize is that what happens is that if you are at time t, okay, if you are in a position n, at a given time t plus delta t, you are in n of t plus some variable s of t, okay? And this s of t can be equal to -1 with probability lambda minus delta t, +1 with probability lambda plus delta t, 0 with probability 1 minus lambda plus lambda minus delta t. Okay? So you can imagine that you say, okay, suppose that I'm here at time t, where I'm going to be at time t plus delta t. Well, there are three possibilities, right? Either I move or I don't move. Okay. And then if you write this and you want to study what is going to happen in a long time, the simple thing you have to do is to say, well, all these steps are independent. Well, I have all these steps. So if I look at a long time, what is going to happen is that I have to sum all these steps, right? So if I want to look at what happens at a time, let's say, t plus capital N delta t, right? This is going to be n of t plus the sum from I equal to 1 to n of s I t. S I, sorry. T plus I delta t. Okay? So basically what I'm saying is I start from a given position t, and then I have to sum all the steps that I did in the process. Okay? And now, in this case, this is very simple, right? Because this is all these s of t are these random variables, okay, which are all independent to each other. They are all identically distributed. So if I look at a large time, what do I get here? Okay. Well, if let's say that lambda plus and lambda minus is equal, this is not exactly equal to 0, right? So what is going to be that term? So if you sum a lot of random variables, what do you get? So if you have a random variable, right, and all these random variables are independent, and you sum many of them, right, and they have mean 0, what do you get? You get exactly 0? Huh? Yes, you get a normal distribution, in that case, if they are of mean 0, around 0, right? A normal distribution that expand, right? This is central limit theorem. Who is not familiar with the central limit theorem? Okay, so the central limit theorems, okay, let's go here. So central limit theorem. So suppose that you have some random variables, let's say xi, okay? And all these xi, and let's say I is from 1 to n, okay? And these are all independent random variables. So the probability distribution of px1, px2, pxn is factorizes, okay? And also let's say that they are identically distributed. So these probabilities, the marginals are the same for all, okay? And then suppose that you want to know what is the value of, let's call it y equal to the sum over xi. Now, y, so if all of these are random variables, so you toss a coin or you, I don't know, you do whatever process, if all these are random variables, the sum is a random variable. Okay? And so you can ask, in general, if you sum to random variables, you will have a distribution of their sum, which can be arbitrarily complicated. Now, the question, what the central limit theorem says, is what happens when you sum many of these random variables. Okay? So when n is very large. Now, this can be done with all the sort of cross on the T's and dots on the I's. But the idea is that when n is large, if this distribution is well behaved, so if this distribution in particular has a finite mean and finite variance, what happens is that this sum, so y is normally distributed. Okay, so follows a normal distribution, and the mean of y is equal to n times the mean of x, which is expected, right? In the sense, well, it's also a joke, it's expected. It's expected in the sense that, of course, on average, if these were determined, if these were not random variables, were exactly equal to their mean, if you sum some numbers, you get, and they're all equal, you get n times. And then the interesting part is the variance, which says that the variance of y is equal to n times the variance of x. Okay? So the interesting result here, the surprise, is that no matters what is the distribution. I mean, the beautiful thing about this theorem is that it doesn't matter what is the distribution of x, you always get a Gaussian distribution. Okay? So you see here that we have exactly the same thing, right? So here we have random variables which are identically distributed. They are independent, this S. Okay? So what we get for large times is, you're not sure? Okay. Huh? The last question?
It's a handwriting issue.
This is X. Ah, okay. This point? Okay, thank you. Sorry. When I was in elementary school for 5 years, the teacher was always saying, write better, write better. And it was saying like on this size, and then the last years was like the full page, you should write better. I tried, but I don't. Okay, so what you have here is exactly the same thing, right? So what you expect here is that this quantity here will be n times the average of this S, okay, plus something which is a random variable, a Gaussian random variable. Well, let me write it and then explain. N times sigma square eta. Okay? So this way of writing is basically a way of writing exactly this result here. So I know that this is going to be a Gaussian random variable with mean equal to the mean of S and the variance equal to n times the variance of S. And so this term, I can write this as this number plus an amplitude, which is going to be equal to the standard deviation of this random variable, which is n times sigma square, where let's say sigma square, it's equal to S minus S, plus eta, which is a random variable with mean 0 and variance 1. Okay? So writing this is exactly equivalent to say that this quantity here, it's a Gaussian distribution, if you want. This quantity is Gaussianly distributed with mean n S times n, where the variance is n sigma square. Okay? Good. Okay. Okay, so what we know is that if I start here and I keep doing these things, what is going to happen is that if I wait, well, sorry, I have to say what is the average of S. How do I have the average of S? Well, I get it from here, right? So what is the average of S? The average of S is equal to
Lambda plus minus lambda minus.
yeah, so it's equal to lambda plus times delta t, which is the probability of having 1, minus lambda minus delta t, and that's it. Okay? And so, and the variance is equal to lambda plus lambda minus delta t minus this term here, delta t squared. Okay? Now, okay. Now, if we put this expression inside here, what we get is that for a long time, n plus t delta t, well, sorry, n plus t n delta t will be equal to n of t plus lambda plus minus lambda minus n delta t plus square root of n lambda plus lambda minus delta t plus another term that I will not write times eta. Okay? So now if I call this capital T, what I get is that n of t plus t is equal to n of t plus lambda plus minus lambda minus t plus square root of lambda plus lambda minus t. Okay? Which is probably the solutions that who is familiar with the random walk. So what this is telling you is that if I start from some position, after a long time, I'm going to be in a position which is Gaussianly distributed with some mean and variance. And the mean is given by actually this, so the position plus this term, okay? And the variance is given by the argument in the square root. Yes?
Is the eta like some kind of noise?
Eta is for me a random variable with a Gaussian random variable with mean 0 and variance 1. Okay?
But what does it signify?
What will it signify?
This is like the sort of the terms that encapsulate the stochasticity. So in some sense, suppose that I start from this position and they repeat the process twice. What I'm going to have is that I'm going to have that the mean is always going to be the same. The variance, I mean, that somehow the realization of this noise is what makes the two trajectories different. Okay? So if I initiate two trajectories, I have to draw two random numbers from a Gaussian distribution, and then that is going to be the result. Okay? So if you want is what makes trajectories different, right? It's somehow what encapsulates the stochasticity.
So if I'm getting this right, when you have two different kinds of eta, you're going to get two different trajectories, but with the same mean and the same variance.
Exactly. So a way to, if you want, you can imagine two ways to generate trajectories, right? One way to generate trajectory is that I say, okay, start from here, and start doing this. And I wait a long time, and then I repeat it. Or I say, I start here, and then I generate one value of theta, or I start here, I generate another value of theta, and then I get the final position. Okay? Questions? Yeah. Yes, good point. So there is a second term, but you see that in the second term, delta t is squared. Okay? So here there is something I put under the carpet, but I should take it out and explain it very carefully. And the point here is that what I'm saying is delta t is small, okay? And the number of steps that I did is large, okay? So n delta t is finite, which means that I'm imagining that these steps are very small, but I'm looking at many, many steps, okay? And so this is the finite time. Right? And then when you multiply this, you get n times delta t squared. So I get t times delta t, but that is a very small number. Okay, so I can neglect it. Questions? Good. Okay, so this is one way to solve the random walk. There is another way in which I can solve the random walk, which is somewhat more, I don't know, which is starting from this equation, and I'm introducing this way because we're going to use them in the two examples that I'm going to build up. So another way to solve this this problem, which is actually provides the final solution, is to introduce an object which turns out to be very useful when you solve stochastic processes, which is the moment generating function. Who has heard of the moment generating function? Okay, so you have a probability distribution, let's say n of t, and then you can define a quantity, a function, which is defined as the sum over n p of nt e to the hn. Okay, this function here has many fantastic properties, which are all written in the notes. For us, there are two things that are interesting. So one thing that is interesting is that suppose that you take derivatives of this g h of t with respect to h, and you set h to 0. Suppose that you take the first derivative. What you do is that when you take the first derivative, you get that this is the sum of n p of nt n h of t. Okay, and if you set h equal to 0, you get the average of n. Okay, then if you do the second derivative, you're going to get the variance and so on and so forth. Actually, for the log of that. Anyway, you get something related to the second moment. Okay, so you get the second moment. Sorry. So if you take the second derivative, you derive twice with respect to h. This is an n. You derive twice with respect to h, and you get the second moment. Right. So this, as the name says, is a moment generating function. In the sense, by taking derivative, you generate functions. Okay, so if you, another way to solve it, which we'll not see, but it's like written out, is to insert this function inside this equation. Okay, so instead of writing an equation for p of n of t, you write an equation for the moment generating function. Okay, and if you do that, you get an equation that you can actually solve for p for gh of t, and you get a solution, and the solutions you get describes exactly what we saw before. Okay. Questions? Okay. So now let's move to a case which has much more ecological relevance. And so I want to show you two basic processes which sort of both describes stochastic version of the exponential growth. And as I said at the beginning, I want to show you that these two stochastic version of the exponential growth are not simple perturbation of the deterministic one. Okay. So the first case that I want to consider is
I had a question.
Yes.
Why is it more useful to write in terms of the moment generating function?
We're going to see it now,
Okay.
actually, because in this case, yeah, I mean, we're going to see it now explicitly. Okay. So the first model I want to consider is what is called is a birth-death process. Okay. And it describes very simply a population where there are individuals that have some birth rate and death rate. Right. Now, if you remember exactly 1 week ago, Danny showed when he introduced the exponential growth, he was saying suppose that individuals have some birth rate and some death rate. Okay, so he was using the word rate, right? Which is by definition something that has intrinsically a probabilistic meaning. Okay, and why do we need to include rates? Because in the simplest possible setting we can imagine that there is a population of n individuals, and this population of n individuals goes to n plus 1 individual, right? When some individual give birth. Okay, and so what is the probability that one individual give birth? Let's say some value b. Okay, so this is what is called per capita birth rate. And the idea is that if all the individuals are independent, they don't see each other, the rate at which we go from n to n plus 1 is b times n. Okay, and similarly, if all the individuals are independent to each other, they are all equivalent, the rate at which we decrease of 1 the population is a death rate times n. This is per capita death rate. Okay? So this defines a stochastic process in the same way as we defined the one before. And you can see that the main difference from the random walk is the presence of this n. Okay? So in the random walk here, we have lambda plus and lambda minus, but these are independent of n. While here, there is a dependence on n. This dependence is very important. And there is also another difference that I did not say explicitly, but it's sort of implicit in this process, is that here we can move to positive and negative numbers, while here we only consider non-negative numbers. Okay? Questions? Okay, so then what we have to do is something basically very, very mechanical, which is to write corresponding equation. And this is very simple, right? So it's exactly the same form where we have b. So the first term, which corresponds to the probability that I had n minus 1 individuals times the probability that one individual reproduced when they were n minus 1, right? So this is the first term.
I had a question.
Yeah.
What do you mean by non-negative numbers? Like if
That n,
okay.
because we don't have minus 3 hippos.
The implication of this that to go from n to n plus 1, it's more probabilistic at higher n. Right?
Exactly. So
Why does it have to do with that?
because if you have, imagine that you have one individual, how much time do you have to wait before it reproduces, right? It reproduces with the rate b, so the time you have to wait is order 1 over b, okay?
But each individual's reproduction rate is dependent on the individual itself and not the community, right?
Exactly, it's independent of the other. But imagine, basically what you have is that if you have one individuals, right, you have to wait until that individual reproduces, right? And it reproduces stochastically. Now, if you have n individuals, all of them reproduces stochastically. So the time you have to wait is the time until the first one among these n independent individuals reproduces. So that is smaller than the time you have to wait for one individual reproduces.
So it's like we have a large number of individuals and each has a distribution of rates.
No,
Which
each individual has a rate. Okay.
And that has a distribution.
A rate is fixed, right? It's a probability per unit time. If you want the time you have to wait for that event to occur as a distribution, which for a fixed rate is exponential, okay? And the point is, if you are drawing one, so basically what you are asking is, how much time do I have to wait before the first events occur, right? If you have one individual, you are drawing one random number for this distribution. If you have 100 individuals, you are drawing 100 numbers. And the one that matters is the minimum one, so it's always smaller, okay? So the first term is, do you agree that this is the first term? Yeah? And then we have, of course, death. And then we have the probability that we add n individuals and either one reproduces or one died, which is B plus T times N P of NT. Okay. Now, if you think about this equation, and I'm answering the question of why do we care about the moment generating function. If you think about this equation is not obvious how to solve, right? Because you have a derivative of time, and then you have a sequence, right? Actually, to be precise, sorry, I was almost forgetting this. This equation is valid, of course, when n is larger or equal than 1, okay? Because, of course, if n is equal to 0, you don't have this term, right? You don't have a term that increases the probability of having 0 individuals from n minus 1. So actually, you have, for n equal to 0, you simply have this term here, right? Which is T P1T. Okay? This is very important, but we'll see it later. Okay? So this equation is not obvious how to solve, right? Directly. And now that's why it's useful to have the moment generating function. Okay? Now here I could start with a tedious derivation that I don't want to do, but it's all written up, but I want to give a gist of the derivation. And the idea is that what you can do is that you can write the equation for this G H of T. Okay? So how do I write the equation for G H of T? Well, I say I want to calculate this quantity here. Okay? And then I'll insert the definition and the derivative. And so what I get is that I get the derivative of P of n, and then I use this one, right? And so for instance, I'll have multiple terms in this sum. And for instance, the first term of this sum will be the sum over n of B n minus 1 P n minus 1 T e to the H n. Okay? Is it clear what I did? And then you have the other term with D, etc. Okay. Now let's look at this term. Right? This term is as complicated as before and as useless as before. But if we look at this term, this is the sum from n. Well, this term exists only from if n is equal to 1 or larger. So the sum from n to infinity of n minus 1 e to the H n P of n minus 1 T. And this one I can sort of manipulate this expression and write it as e to the H sum from n1 to infinity n minus 1 e to the H n minus 1 P of n minus 1 T, which I can write as e to the H sum from n0 to infinity n e to the H n P of n T. And then this term I can write it as I could write it as a mean, but I can also write it as a derivative with respect to H, right? So this term here, it's a derivative of EHN with respect to H. I just realized that H and N looks the same letter from far because this is very small, but this is EH, the derivative with respect to H, G of HT. Now you can repeat this for the other terms, but what you see is that you start from something that, well, it's a complicated equation with a sequence, and if you write with respect to this, you get a partial differential equation, right?
Yeah, just in clarity, so B is a negative number.
No, this is a positive number.
So then how is that second, the dp over the dp over dt, like second equation over there, when n is 0, how is that a positive number?
Because this is positive,
Yeah.
and PO1 is positive.
Yeah, but you're saying that even though you have 0 people, you have growth.
No, no. This is telling you what is the probability. How does the probability of having 0 individuals change over time? I've not commented this yet because this is the sort of final surprise. But the important point here is that here you see that the probability of having 0 individuals can only increase over time, cannot decrease. Okay. But here I wanted to comment on the technical part. So the way to go with this is that basically you introduce this and you get a partial differential equation. Now, when you have these, there are all the tools, blah, 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 to solve this. And so you can solve an equation for, you can solve this equation, basically. You write all these terms in terms of, you use whatever methods. Okay. And so what you can find is at the end, some expression for your GH. Your GH of t. So you have some expression of this h of t, which it's written in terms of the birth probability and the death probability. Okay, and then what you can do with this expression here? Well, you can take derivatives and get the moments, for instance, right? So you can take derivative and get the moments of your distribution, right? And for instance, if you say, I calculate the GH of t, the h, and I set h equal to 0, what you get is the average n, okay? And if you do that, you substitute in this expression that I didn't want to write. You get n0, where n0 is the initial condition. So you say, I assume that my population at time t equal to 0 was equal to n0, and you get e b minus d times t, okay? Which, okay, so you say, okay, all this business to get what we already knew. So this, what is this solution? Is exponential growth. It's exactly the equation that Danny wrote, right? So it's is exponential growth with growth rate, which is equal to the difference of the birth and the death rate, right? And then what you can do is, in addition to this, you can write so I mean, what is interesting about this is that, well, depending on whether the birth rate is smaller or larger than the death rate, you have that this expression increase over time or decrease over time, right? So let's say that you start from some initial population, I don't know, n0 equal to 1. This increase exponentially if b is larger than d, and decrease exponentially if b is lower than d, okay? And now, okay, we have the mean. This is like consistent with the simple deterministic solution. Then what you can do is to calculate the variance of this distribution, right? So what you can do is to ask, okay, what is the variance of this? And so you obtain this by taking second derivatives of this quantity. And if you if you calculate the variance, you have basically two solutions, right? So you have to distinguish what happens for b larger than d or for b lower than d. So if the birth rate is lower than the death rate, what you get is that for large times, so I'm interested, for large times, the variance tends to 0, okay? If the birth rate is larger than the death rate, what you get is something like n naught b plus d over b minus d e to the b minus d times t, okay? Times a 2, okay? So what you get is, if the birth rate is smaller than the death rate, the variance goes to 0. If the birth rate is larger than the death rate, the variance goes to infinity, okay? And now, if in this case here, if you ask, okay, what I'm having here is something that has a mean that increases exponentially over time. Okay, and there's a variance that increases exponentially over time. And what you see is that these increase exponentially over time with an exponent that is proportional to 2. So the coefficient of variation tends to a constant when t goes to infinity and b is larger than d. Okay? So when b is larger than d, you have a distribution that has a mean that increases exponentially over time, and the variance also increases exponentially over time, and the width of this distribution sort of becomes relatively fixed, right? So the variance divided by the mean becomes converged to a finite value. Okay? Questions about this? Now, what is the interesting message here is that we can say, okay, this is, I have these two distributions, and I have these moments. But now the fact that the coefficient of variation goes to a constant, it implies that as you grow with the population, you cannot somewhat neglect stochasticity, right? It's not that the relative impact of stochasticity becomes smaller and smaller, right? It has a sort of fixed effect.
What exactly is that?
This one, yeah.
This one is the variance divided by the mean.
The square of the mean.
The square of the mean, yes, is the
So
variance.
what exactly does it?
What it means?
Yeah.
So this is called coefficient of variation, and it's something that suppose that you have distribution that has mean 10, okay, and the distribution that has mean 1,000. The variance, or the standard deviation, which is like the square root of the variance, tells you typically how much you deviate, okay? So if you have a standard deviation equal to 10 and you have a mean equal to 10, or if you have, imagine that you have a distribution with mean equal to 10 and standard deviation 10, or you have a distribution with mean 1,000 and standard deviation 10, what you can imagine is that the second one with mean 10 and standard deviation, mean 1,000 and standard deviation 10, relatively has a smaller variability, right? Because you will be between 990 and 1,010, while in the first case, you'll be approximately between 0 and 20, okay? So the ratio of the standard deviation and the mean, or the variance and the mean squared, tells you how much variable is the distribution, okay? And what we find is that as time goes on, this doesn't go to 0, right? So it's not something that becomes negligible, yes?
So what would happen if B is equal to B? Yeah.
If B is equal to Z, it's interesting, it's called the critical case. And what happens is that this quantity increase linearly with T, okay? Yes. Yes? Is no, the coefficient of variation, yes, it has a not in the denominator. That's true. It depends on the initial condition. Okay. And I'll explain why in a second. So now this is like sort of finding the mean and the variance. But there is something that we briefly mentioned before, which is about the probability of having 0 individuals. Yes?
Then if you start with a higher initial population size, the lower chance of going extinct.
I'll comment that now. So the important point here is that, as we said before, there is this probability of having 0 individuals in at time t. Okay, so we say that there is this quantity, right? And in the equation that we wrote, this quantity could all increase, right? And this is again Spallanzani, right? If we hit 0, if for some reason we have 0 individuals, okay, we'll never be able to have one individual again in this process. Okay, and so what we can ask is, what is this quantity? Okay, now this quantity can be obtained from the moment generating function by sending h to minus infinity, because in that case, I erased the definition, because in that case you have, this will be the limit of h going to minus infinity of the sum from n to 0 to infinity e to the ht p of nt as the hn. And the only terms that survive when h goes to minus infinity is the one with n equal to 0. So it's p0. Okay? This is p0t plus sum from n to 1 to infinity e to the hn p of nt. Okay? And so this in the limit goes to 0. Now, you can calculate this quantity. Okay? And in particular, you can calculate what is the limit for time going to infinity of p0t. Okay? Which is the probability of being extinct in the long time limit. Okay? Now, if you calculate this quantity when the death rate is larger than the birth rate, what do you think is going to be this probability? 1, right? So P extinct is going to be equal to 1. Okay? Why? Because you are, and you see these in the moment, right? What happens is that the mean is going to 0 and the variance is going to 0, because basically with probability 1, we are going to be equal to 0. So mean and variance are both going to be equal to 0. Okay? Now, the surprise is what happens when B is large, well, yes, B is larger than D. Okay. In that case, what is the probability to go extinct? Well, you could say I have a process where the birth rate is larger than the death rate, the mean is increasing exponentially, so 0. No, otherwise I will not be here. So the probability, you can calculate it, it becomes B over D to the n naught, where n naught is the initial condition. Okay? So if you want, you can plot this quantity as a function of D over B. And what you have is that the probability of being extinct, here you have 1. So below 1, sorry, over. Yes, thanks. So below 1, yes. Yeah, I prefer like this. Okay. So below 1, the birth rate is lower than the death rate. So here, the birth rate is lower than the death rate. Here, the death rate is larger than the birth rate. Okay. 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 So here it's equal to 1. And when you hit 1, this decrease as B over D to the minus n naught. Okay. So what this means? It means that, well, this function here, if you increase n naught, it will become more and more sharp. But the idea here is, even if the birth rate is larger than the death rate, what happens is that you have a finite probability of going to extinct. Okay? So you have a probability that is not like negligible. Okay? It becomes negligible if you start from a large initial condition. So sort of going backward, suppose that you simulate a trajectory. How does a typical trajectory looks like? So suppose that you start with some n naught, let's say n naught equal to 1. So you have n naught equal to 1, and then you are in a situation where B is larger than D. You have n, and you have time. Okay, and we look it for large times. So what we have is that change color. So what we have is that we have the average. Okay. And how the trajectories look like? Well, the trajectory are not following closely this average. What does it mean? It means that you have trajectories that sort of will grow exponentially and more or less will be around this average. And then you have trajectories that go extinct at some times. Okay. And so you will have a finite proportion of the trajectory that grows and a finite proportion of the trajectory that goes to extinction. Okay. Now, the combination of this trajectory, so the average is equal to n, but the average, it doesn't tell you that you have these two very different families of trajectories, right? The one that are actually growing exponentially and the one that are going to zero. On average, they grow trajectory, but the average doesn't tell you that you have sort of these two alternatives, okay? And the fact that you have a finite coefficient of variation comes from the combination of these two processes, right? The fact that you have some trajectories going to zero and some trajectories going to growing infinity, okay? Yes?
Maybe it's an obvious point, but I'll say it anyway, and you can have a discussion, which is a little bit trying to connect what the units of these n's are and how we've been comparing it last week when we've been talking about densities and abundances and so on and so forth.
Good point. So the point is, here what we are considering is that we are considering discrete number of individuals, okay? So here, the sort of source of stochasticity is the fact that we have discrete number of individuals, okay? And we are following them one by one. And this is important because we are starting with an n naught, which is, let's say in this case was 1, but it's finite. How does it compare with last week? Well, last week what we consider is somehow we consider very large populations. So populations where, in particular, n naught is very large, okay? So if n naught is very large, you can see that this is negligible, right? So if this is like smaller than 1, the argument is smaller than 1, and n naught is very, very large, this becomes effectively 0, okay? Because what happens here is that you have some unlucky trajectories that makes you to go extinct, right? Suppose that you start with one individual, right? And one individual has a birth rate which is twice the death rate, okay? It's still possible that it's gonna die before reproduce, okay? The point is, if you have 1,000 individuals with a birth rate that is twice the death rate, the probability that all they're gonna die before reproducing is very small. And the probability that all their children are gonna die before reproducing is very small, right? And so it becomes negligible. So the reason why what we did last week makes sense is because there are contexts in which you can neglect these because the initial population, let's say, if you have exponential growth, is very large, okay? But there are other contexts when you cannot neglect these. For instance, suppose that you have a mutant and you want to know the fate of this mutant, right? Even if this mutant has an advantage over the resident population, so it will tend on average to grow exponentially, initially it comes one individual, okay? So you can have many mutations which are beneficial, which on average will grow, that actually go to extinction, okay? Other questions? Okay, so this is one example of a process where you have a source of stochasticity that in this case, this source of stochasticity, when it's due to the discrete nature of individuals, is called demographic stochasticity, right? It's due to the fact that individuals are discrete, so each of them is reproducing independently. In this case, which is very simple, you still see instance where the average behavior and the typical behavior, so what you see if you simulate this trajectory, differ. Okay? What I want to show you now is another example where this also happened. Okay? Questions on other questions on this process? Yes.
So if I understand it right, what you're saying is that if n were to change by a continuous small value, you would not necessarily see it.
Okay, the answer is yes. And the reason is, if you can make that approximation, what does it mean? What is the question asking? Is suppose that this can change continuously. What does it mean change continuously? You have, I mean, suppose that you have a bacterial community and you have 10 to the 9 cells in a milliliter. Well, you're gonna have, I mean, a number, right? An exact number. It's gonna be 10 to the 9, whatever. It will be 1 billion, 4,500, whatever, right? You have a number and you can count this cell, right? And they're gonna reproduce and increase one by one. Now, the point is that in that case, the initial conditions are so large that somehow the discrete nature of this jump does not matter, right? So going from exactly, let's say 1 billion and 1 billion plus 1, it's a very, very small change. So somehow you can make this different continuous, okay? But it's still true, right? It's still true that in a bacterial community, you can have demographic fluctuations. And it's very unlikely that with these demographic fluctuations, you go immediately to 0 if they were growing. But it's still true that this can play a role, right? If the population is to small enough values, okay? Other questions? Okay. So this is one way, one sort of source of stochasticity in population dynamics, okay? Which is due to, as I said, to the fact that we have a discrete number of individuals. Now, there is another source of stochasticity that we can consider, which is not due to the fact that individuals are discrete in nature. We can imagine that we have a very large population, but are due to the fact that the environment is fluctuating, okay? So in that case, what we are going to consider is a case where we have a population which is growing exponentially, okay? And is a large population, so we can neglect the discrete nature of the individuals. But this population, the growth rate of this population is subject to fluctuations, yes?
So yeah, another question is, so the effective
Can ignore demographic stochasticity when the initial conditions are really large. They have large population size, right? But what if there's like a logistic growth? This assumes
Yes.
that there's infinite
So, yes. So in this case where we have, sorry, go ahead.
No, so I was asking like, so in the logistic growth, initially when there are when it's at low density is exponential growth, but at higher densities, it's sort of leveling off. So I'm guessing like the extinction rates will change with the population size itself as opposed to here.
Let me answer your question. So the process you have in mind is a process where you, for instance, and you could write it explicitly, is a process where you can say, I have a birth rate. The rate at which I go from n to n plus 1 is b times n. And then I have some sort of density dependence, which I can put, for instance, in the death rate. And so I say that this is the rate at which I go to n minus 1 is dn, is like before, but then I have a density dependence. So if there are more and more individuals, is more and more likely to die. So if you want, the death rate per individual, per capita, is something that is not just the usual death rate, but also depends on the density of individuals, increases as the density of individuals goes to. So if you write, in this case, the equation, I mean, okay, so the point here is that if the population is very large, okay, this equation here behaves like logistic, right? It's like a logistic equation. Now, what does it mean if the population is very large? So the first point is, what is the initial condition, as you said. So if the initial condition is very small, right, effectively at small densities, this term can be neglected. So a small density grows exponentially, so you are subject to fluctuations. But the other situation is that you are growing and you are going to go to some carrying capacity, right? Then what matters is how big is this carrying capacity, okay? Because here you have two competing forces, right? You have a force that pushes you back to this carrying capacity, that make you stay close to this carrying capacity, and then you have fluctuations, right? And so you are not going to be exactly at carrying capacity, but you fluctuate around, okay? And it's always possible that one of these fluctuations by chance drive you to extinction. Now, the probability of this to happen depends on how far you are from zero. And in these processes where you have like a well-defined stable state, this probability goes to zero very rapidly with the population size, okay? Or better, let me say another step to qualify the situation better. In this case, if you are in zero and you are extinct, okay, in the long time you will always hit zero, okay, in this case. But the time it takes to hit zero is exponential in this size here, okay? So you will arrive at that because this is finite, but the time it takes, it's very, very long. Okay. Other questions? Yes. Well, in this case, you can imagine that you start from some initial condition with 1 individuals, 100, whatever you want. Okay, is well your choice in some sense. Okay. Other questions?
Whether we reach the carrying capacity or not depends on the initial
So the probability, yes. So the probability to reach the carrying capacity to sort of grow and pass this initial phase depends on the carrying capacity. Okay, but there is a difference, which I said it incorrect at the beginning. So if you have exponential growth, you have these trajectories that grow exponentially, right? And tends to go to infinity, keep growing. In this case, you sort of level off and you fluctuate around this value, which means that sooner or later, you will always have a negative fluctuation. Now, the time you have to wait for this to happen grows very rapidly with how far this condition is, how far the saturated, the stable population is, okay? So meaning that you're gonna spend a very, very, very long time fluctuating around this value. Other questions? Okay, I have 5 minutes. And I'm thinking of what to do. Well, I'll tell you this story. So very quickly. So in this case, what we imagine is that there are environmental fluctuations. So we are imagining that there is this population. Can I finish in 10 minutes since we started later? Thanks, Mathieu, for saying yes. That was exactly the answer I wanted. So in this case, what we imagine is that what is fluctuating is not something due to the discrete nature of populations, but is actually the growth rate itself, okay? And so if we don't have fluctuations, we have an equation that looks like this, right? Say a growth rate times the population of time t, right? Sorry, let's say n, to be consistent. Okay, so, right? So this is the way we derive exponential growth. And if you want, you can interpret this as an average over the demographic stochasticity, but it doesn't matter. Now, what we want to consider is a situation where this depends on time, okay? And in particular, we want to consider a situation where this depends on time. Sorry. This depends on time because it fluctuates, okay? it fluctuates around some value. Okay. Now, for simplicity here, one can do the derivation in generality, but let's consider that we consider a discrete process where we set delta t equal to 1. Okay, so I'm going to say that this is discrete, and I'm going to write t n of 1 plus t r of t n of t. Okay, so we have this small time step, but we consider it like in units of these small time steps. Now we want to solve this process here, and the way to solve this is to write, well, we can write this as, we can take the log of this term. And if we do that, what we get is, this is log n of t plus log 1 plus r of t. Okay? So this means that if we start from some initial condition, the log of n of t will be equal to the log of n of 0 plus sum I from 1 t log of 1 plus r I, 0 to t minus 1. Okay? Now imagine that this is a random variable with some mean and variance. What is going to be this? Where did you see this equation? Suppose that t is large, right? This is a sum of some random variables, right? And let's say that the growth rate is some independent random variable with some mean and some variance. Yes, okay. Can I change notation? Sorry, let's call this G for one pedagogical reason, which is, okay. Same thing, but different notation. So what you have here is that you have a sum of some random variables, right? And so this quantity here will have a right. We'll have a mean equal to, I mean, it will be t times the mean of this variable here. So the mean of log 1 plus g, which I call r, okay, plus square root of t times some variance, which corresponds to the variance of this term, times a random variable eta. Okay? This is the same as before. Okay? What this is saying is, if we have a population growing exponentially with this rate that is fluctuating, that is stochastic, if we look at the log of the population, this is doing a random walk. Okay? So this is exactly equivalent, right? Because I'm saying the population at times t plus 1, the log of the population at time t plus 1 is the log of the population at times t plus a random variable. Okay? So then we have these questions.
How do you get the log of 0?
Sorry, these I did 2 steps in one. So here I wrote, no, this is the equation, and then I iterated this, right? Because you can write this quantity, and then this can be written as log, what is log of n of t? Log of n of t is log of n of t minus 1 plus log of 1 plus g of t minus 1. This term is this term plus log 1 plus g t, right? Which is this term here. And then I can write n of t minus 1 as n minus t plus 2, blah, blah, blah. And then I get this solution. Okay? Questions?
How does the eta come about naturally? Is it natural?
Because of the central limit theorem. These are random variables. They are independent. Okay? So this sum here, it's a Gaussian random variable with some mean some standard deviation. Okay. But then this is just a way. Okay, I understand the confusion. This is just a way to write these things. It's equivalent to say that this whole thing, it's a random variable which is Gaussian with mean RT and variance T sigma squared. Okay, you can write a Gaussian random variable like this as a constant plus a width plus a random variable which means 0 and variance 1. Okay. So what we find here, the solution is the following: is that in this solution here, what we get is that n of t. Now I can take this expression here and take the exponential of both sides, and I get that n of t is equal to n of 0 e to the rt plus square root of t sigma square eta. Okay? Yes. Now, I ask you, what is the average of this process? Okay? You take the average of this process, so you take n of t average. Okay? What you have is that you can write this as n0 e to the rt times the average of square root of t sigma square eta with respect to eta, when eta is a Gaussian random variable. Okay? If you calculate this average here, this term here is equal to sigma square over 2t. Okay? So what you get is that the average number of individuals in this process grows as e to the r plus sigma square over 2t. Okay? So it grows with a growth rate which is r plus sigma square over 2. Okay? Then I have also this expression here, and I can ask you, okay, I have this expression, eta is a random variable, but what is the limit for t going to infinity of n of t? Okay? If you take the limit of n going to infinity, you see that this term here, right, grows much faster than this. So this, well, the behavior for large times, let's say, times much larger than 1 over, well, when t goes to infinity, grows as n0 e to the rt. Okay? So here we find something puzzling. Right? We have an expression, this is an exact solution. Okay? And we have a solution for the average and a solution for the typical situation when the time is large. And we have that the average grows much faster than the typical solution. So if you plot, let's say, in log n, what you have is that
expression for infinity. Like
I just take the limit for large times. You see that you have this term here, which grows as t, and this term, which grows as square root of t, so it's negligible. Okay. So if you have, well, some initial condition, here you have the average solution, okay, which grows like with some rate r plus sigma square over 2t. And then you have the large time limit, the typical solution, which grows with a different rate, okay, which is rt. Okay. So what is happening in this case here? What is happening in this case here is that if you look at the trajectories, if you simulate this process, what you see is that the trajectories are around this value. Okay. But the point is that there is one extremely rare trajectory. I mean, there are very, very, very rare trajectories which grow very, very rapidly. Okay. And basically, when you take the average of these trajectories, the one that dominates the average are these ones. Okay. But if you simulate your process for large times, you're never going to see them. Okay. They are exponentially rare, but they are exponentially favorable, right? And this being exponentially favorable in the average dominates over the fact that they are rare. But then if you look at a typical trajectory, it doesn't behave like the average. Okay? So in some sense here, we are in a process where we have a population that experience an environment that is stochastic. Okay? And so let's say that the environment can be favorable or unfavorable. Okay? And they are growing exponentially. So when it's favorable, they multiply of a factor. And somehow the average is dominated by this very rare trajectory where the environment is always favorable. Okay. But the typical trajectory doesn't feel that, right? The typical trajectory feels a mix of the two. Okay.
By typical, you mean is it the average? And
typical, I mean, you simulate this process and you look how the trajectory looks like. You simulate again and you do that again. Okay. For large times, you see this behavior. To be even more precise, to see these trajectories here, you have to average over a number of trajectories which grows exponentially over time. Okay? Because this is a very, 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 very rare trajectory. So if you simulate your process 10 times, 20 times, 15 times, 50 times, you will see trajectories like this. As the time goes large enough. Yes.
But those are also exponentially growing, right? All
trajectories are exponentially growth. This is log n, so you can imagine this like growing up. Yes.
But how do we deduce the proportion of which trajectories are what kind?
No, this is not, you don't use it, right? If you simulate the process, you're gonna see, many trajectories. And so if you fix time, you will see many different values, right? The point is, as this time increases, okay, the more and more trajectories are around this value, okay, and becomes more and more rare to be like a large fluctuations. But the fluctuations you get are more and more rare, but are larger and larger. So when you take the average, these very, very rare fluctuations dominate. Okay. So you have basically this jackpot solution where this population, there is this very rare, super favorable environments, and what happens there is what dominates. Okay. So to summarize, because I took 5 minutes more. So this shows sort of two examples where we have a very simple baseline, which is exponential growth. And we introduce stochasticity in two ways. One is demographic stochasticity, so fluctuations due to the finite nature of the individuals. And one is environmental, due to the fact that the environment fluctuates. And in both cases, in different ways, we saw that the average behavior does not necessarily correspond to the typical behavior. Okay. Now, there are limits in which the two can correspond, but in general, we cannot neglect this. Okay? Yes?
Just to type back to saturated growth, we wouldn't see jackpot solutions if there was saturated growth.
Yes, correct. But still, if you have saturating, we'll see that 3 days from now, still, if you have saturating solutions, the effect of there is another effect that the noise, the expectations values are not the ones which corresponds to setting the noise equal to 0. Okay. Yeah. G in principle can be negative, can fluctuate, let's say. We are assuming that the average, okay, so the average of this term here, okay, is positive.
Because I was wondering if you have trajectories that do exponentially worse as well in unfavorable environments as opposed to the average.
It will be, let's say, if you forget about what we said in the first class, the first part of the class, so that individuals will go to 0, is the same. It doesn't matter whether it goes up or down. Okay, you will still have that this line here will be well above the other one. Okay. Yes.
Is this related to the fact that now N of t is not like the randomness is not just normal, it's sort of log normal because you have
Yes. Yes, it's the same. Yes, exactly. It's the same. See you tomorrow.